Hello, everyone. I'm Jonas. I'm in the Algorithms and Complexity group, and I am a sort of maybe practicing, I guess, a theoretical quantum computer engineer in some ways. And today I want to talk about some work that I've been sort of doing recently. And if you're interested in the details, which I will not provide, you can find it at this archive link. But I want to talk about something called classical shadows, which is a sort of fairly new concept in, I guess, quantum characterization theory. And I want to show how it's it's an exciting new tool for characterizing noise and errors in quantum computers. But I want to sort of emphasize broadness of appeal over technical detail in this talk, so I won't be giving too many equations. I tried to turn as many as possible of them into drawings, so let's see how far we get with that. All right, but let's first sort of set the scene. The fundamental problem with quantum computers is that they don't work very well, and it's not clear, it's going to take a lot of effort to make them work. So in a sort of ideal theoretical world, a model of a quantum computation would look like this. You have some sort of initial register of qubits, which are like tiny little vectors in a vector space, and you can act on them with quantum logic gates. And some sort of this initial state will transform into a final state that will hopefully encode a solution to a problem that you have. So this is a very abstract, sort of generic view of ideal quantum computation. If you try to do this in practice, you turn these registers into little electrons, and you turn these gates into like microwaves that you send to these electrons to try and change their state. All kinds of things tend to go wrong. So your state preparation might go wrong, your electron might be in the wrong state to begin with, or your gates might go wrong, like you might send a microwave pulse that's too long or too short or aimed at the wrong electron, and things just generically don't go very well. This is, of course, also a problem in classical computation, but there it's more or less solved. I'm not sure what the error rate of a logical gate in a classical computer is, but it's very, very close to zero. Whereas for a quantum logical gate, at this point, it's around 1% of the time, depending on how you count, a logical gate in a quantum computer will fail in some interesting and non-trivial way. So there's a real problem of trying to figure out when these things fail and trying to figure out how these things fail. Okay, so this is sort of the mission statement, I guess. Quantum computers are noisy, they have errors, and if you want to do anything serious with them or build even bigger ones, you have to take this noise into account explicitly. And this is an interesting theoretical challenge because quantum computers are they're fairly complicated objects. They're composed of these really high dimensional Hilbert spaces, even abstractly. So learning anything about this noise based on the information that comes out, like the classical information that comes out at the end, is a non-trivial task. And this is what I would sort of call the nascent field of quantum characterization. People sometimes call it QCVV, but we don't do a lot of verification and validation yet. So it's mostly characterization. And today I want to talk to you about sort of characterization of the dynamic bits of a quantum computer. So I told you that state preparation can go wrong and that gates can go wrong. And then there's also measurement at the end that sort of classicalizes your quantum information, and that can also go wrong. But sort of the dynamic bits are the most important parts, because if you write really long algorithms, most of the errors that are going to happen are in a gate. So these are sort of the things that we want to characterize the most. So that's sort of the broad goal of today. And the plan is to show you like a little bit of that, namely how to use this new concept called classical shadows to sort of make some headway into this particular problem. Yeah, so we want to characterize quantum processes. So I'm going to use the words gates and processes and channels sort of interminglingly. I'm going to try and be as consistent as possible, but you're going to hear me say these three words. They all mean the same thing. They're like a noisy logical gate in your quantum computer, or a noisy whole circuit. Like we're just going to slightly jump up and down between these two levels of abstraction. All right, so where does noise characterization sort of fit in the tool chain of quantum computers? So as I said, this is sort of a fundamental part of building them. So currently people are trying to, in a lab, build sort of quantum logic gates out of indeed electrons and microwaves. And a big part of doing this in practice is using characterization tools, these sort of abstract algorithms that extract information out of your noisy quantum computer to sort of optimize the probabilities of error in these logic gates. So you have this sort of nice feedback loop that where you use this characterization to inform optimization of your logic gates, and then you characterize them again, and you keep doing that until your logic gates are very good, and then you think, okay, I'm going to try and do some quantum algorithms, and then you realize that there are limits to how well you can make your logic gates, and quantum algorithms are usually very long and complicated. So between your actual problem solution and quantum algorithms is more noise. This is still, even if you have you throw all the engineers you have at this sort of initial problem, there is not really a hope that you're going to solve this as well as we did in classical computers, because quantum computers are sort of inherently more noisy. It's a little bit more tricky. So one way to solve this here, this sort of from algorithms to solutions, the noise problem, is by quantum error correction, but we're not going to talk about that because it's hard, it's sort of a future thing. Then there's quantum error mitigation, which also has this sort of characterization loop attached to it. But I guess I mostly just want to show that this shows up in many places, and that what I want to motivate here is that we want to take an abstract view on these tools, that we don't want to do characterization just at the level of the physics, but really at the level of, oh, I have an abstract quantum computer that teaches me something, and I learn something about the noise, and then I can sort of at an abstract level use that to either enhance my logic gates or try to mitigate errors as they arise. So those are sort of the two places where it fits. And before we go into actual characterization tools, I want to set the stage a little bit more, because I know that a lot of you are not quantum information theory people, so you might be very confused whenever I say, oh, state and quantum channel and quantum process. So I'm going to make these things extremely concrete for you using math. So quantum characterization is nothing more or less than learning properties of high-dimensional positive linear operators, so symmetric matrices with positive eigenvalues, in some sort of weird access model. So we're going to be talking about sort of query complexity to learn certain properties of linear operators, essentially. So you can, in a sense, you can forget everything you know about quantum computing and just think of this as a problem where we want to learn certain properties of matrices. So I can think of an n-qubit quantum state, a noisy one, as more or less a 2 to the n by 2 to the n positive matrix. And the key thing to notice here is that this matrix is relative to the number that we care about, which is the number of information carriers. This is a huge matrix. So this is our first sort of major problem, is that the things that we want to learn are always massive, massive objects. So for more than 10 qubits, this already becomes really impractical to even write these things down. So this is a problem that you're always going to try and work around. And then if you say, okay, quantum states are just matrices, then it turns out quantum gates, which are your logic gates, but also the circuits that you compose them of, are more or less unitary matrices. So also really large unitary matrices that act by conjugation on these quantum states, or density matrices, as we sometimes call them. So that's sort of the fundamental mode of quantum computation, is you have some big matrix and then you act by conjugation with two other big matrices that specify your algorithm. A noise process is a slightly more general version of these unitaries. So any physical process abstractly is more or less a linear transformation of these density matrices. And sort of in the abstract view, the only thing that we're going to ask is that this preserves positivity. So that it sort of preserves the physicality of these density matrices. So apart from that, these things can be essentially arbitrary, apart from the fact that we also want them to be linear. So whenever you see a lambda, which is sort of an abstract representation of a quantum noise process, could really be anything, you can think of this as a 2 to the 2n by 2 to the 2n matrix. So the goal of quantum process characterization is nothing more or less than learning some property of these really huge 2 to the 2n by 2 to the 2n matrices. So that's what the rest of this talk is about. And the way we can learn things about these states and these processes is by doing what we call measurements. And measurements are sort of special distributions that we get access to. And this gets a little bit technical, but sort of the query model that we allow ourselves is that if we have a quantum state, we can measure, and this gives rise to a sample from a distribution that is more or less given by, let's restrict ourselves to just saying, I have a distribution that's just the diagonal elements of this density matrix. And I'm gonna, if I have a quantum channel, I can sort of have this generic query model where I can input a state into the quantum channel, and then I can make a measurement, and I can sort of sample from the resulting probability distributions. And so the goal is, given such probability distributions for input states that I can choose and output measurements that I can choose, what can I learn about lambda? And this is an important problem. So people have been thinking about it for the better part of 25 to 30 years, which is about as long as quantum computing exists. And over this time, more or less a sort of a dichotomy has appeared between the types of characterization protocols that exist. And I like to call this is sort of a no free lunch problem in some sense. And of course, we're going to try and get free lunch. So here, this is sort of a graph where I've put a representative sample of all kinds of characterization procedures. And the names don't really matter, but they sort of split up roughly into 2 types of protocols. One is, which are ironically called benchmarking protocols. This is a historical misnomer. They're all named after something called randomized benchmarking, which is really a characterization protocol and not a benchmark, but we can argue that problem later. And their sort of overriding collective identity is that they are efficient, in the sense that even if I have an n qubit system, so I'm trying to learn something about a 2 to the 2n by 2 to the 2n quantum noise process matrix, I can do that efficiently. And by efficient, I mean sort of in a polynomial in n queries. And often this is a small polynomial, so it's really even efficient in practice. The downside of it is that these protocols collectively only teach you extremely averaged information about your quantum channels. So you don't get access to like individual elements of this matrix. You get access to something sort of extremely average things. A typical example would be the trace. We can estimate the trace of a quantum channel. We have this big matrix and we can learn what its trace is, more or less normalized by the dimension to make the numbers small. But this is it gives you some indication of noise, but it tells you basically nothing about the specificity of the matrix. You get one number out of this huge object. And then on the other hand, you have tomographic methods, which are sort of here. And these are sort of, they take the complete opposite approach. There, your goal is to get extremely detailed information. So for instance, what you are going to do is by carefully inputting states and measuring, you're going to try and reconstruct every element of this giant matrix. And this is something that you can do in practice. The problem is that you are going to have to query your quantum channel. So, prepare a state, apply the channel, measure. You're going to have to do this, at least as many times as there are elements in your quantum channel. So this is a big, unpleasant exponential. And there is sort of no sort of in between, or even better, sort of free lunch, where we get a lot of relevant information in a polynomial number of samples. And we would like to have free lunch. So the question is, can we get free lunch? And I think if this talk was in person, there would be free lunch, so this joke would land better. And it turns out that we can actually get free lunch. The only downside is that the lunch is kind of cheapish, so it's not very good lunch. And I'm going to try and show you how to get lunch. And the way we're going to do that is we're going to combine 2 ideas. One of which is called state shadow estimation, which is a free lunch protocol for state tomography, and we're going to inject that into a process procedure, which is called randomized benchmarking. And together, the both of these will give us something that lives more or less in free lunch land. And that's the topic of the paper that I mentioned earlier. All right, so now we're going to get slightly technical. So this was sort of the broad setup. I've said what I was going to do, and now I'm going to do it. So let's talk about shadow estimation of quantum states, so not of processes. This is kind of important. So if you're interested in learning aspects of quantum states, which again are also huge matrices, you can also do tomography by measuring it in various different bases, try to reconstruct this 2 to the n by 2 to the n matrix. This is very inefficient. So you need a lot of copies of this density matrix. You need to prepare it lots of times. But it turns out if you don't want to fully reconstruct it, there is actually a really interesting idea, which is, I didn't write it down, it's called shadow tomography. And this is where, so the idea is in fact the opposite. So instead of saying, I want to learn this whole state, the only thing you're interested in is, okay, I have a list of things that I'm interested in. And in quantum mechanics, these are called observables. So this is a list of pre-specified properties of your quantum state that you might be interested in. And then it turns out that if you specify those in advance, then there is a really beautiful protocol due to Aronson, which is about 15 years old now, that gives you all of the answer to all of these questions without actually ever writing down this full matrix. And it gives you this answer using log m. So this is very efficient in poly n queries of your density matrix. So this is technically efficient, even though you're trying to do a lot of things. You're learning exponentially many sort of averaged quantities. The problem with this protocol is that it has really complex entangled measurements. It's extremely sort of non-constructive. No one has ever done this in practice. But so 15 years later, and this is really sort of the starting point of my own work, there was a really beautiful paper, it's about 2 years ago, by Huang, Keng, and Preskill, Kung, I think, actually, where they said, if we don't restrict ourselves to a set of arbitrary M observables, we say, okay, we're going to learn some restricted set, and this restriction turns out to be fairly weak, then we can make this sort of really complicated protocol into an extremely simple one. And for the people that are sort of into compressive tomography and learning things about large density matrices, or about large matrices sort of classically, you are going to find this, I think, quite appealing. So the thing that they did is the following. It's a very simple protocol. So you want to learn this number here, which is your density matrix times some observable, which is also a positive matrix, and you want to sort of learn this trace. So what they said was, okay, we're going to insert more or less an identity here, which is this UXX U dagger. I'm going to plug that in there. There's some averages here that we don't care about. And then we are going to take this sort of abstract entity and we're going to do one bit of it, the colorful bit, on our quantum computer. We're going to call it the state shadow. So this is a procedure, right? It's a density matrix. You apply a unitary, and then you measure in a basis. So you do some sort of, and this unitary you sort of pick at random. So you essentially measure an arbitrary diagonal of your density matrix. And then you sort of, on your classical computer, you invert this operation, and then you sort of look at what the effect of your observable would have been had you done it. And it turns out that this is more or less a tautology, so these things are equal to each other. So you can estimate all of these things, classically compute all of these things, take the average, and get this number out. But because the thing that you're doing on the quantum computer is essentially independent of the observable that you're trying to compute, you can just do this experiment once, and this is really the rub. You do this one experiment, and then you do in your classical computation the reconstruction for a whole bunch of different observables. And by essentially the union bound, sort of your standard probabilistic technique, you can show that with a log m overhead, you can compute all of these observables from this same set of data. And that's a really beautiful trick. And you have to do a fair amount of mathematics to prove that it works. And it turns out that it works as long as you reasonably restrict your observables. And here, yeah, don't worry about this too much. It turns out that you need to restrict your observables in the Hilbert-Schmidt norm. So the trace of their square has to be bounded, which is a little bit awkward, but a lot of interesting observables actually have sort of bounded Hilbert-Schmidt norm. So this is an extremely useful thing. The problem is that this does not work for quantum channels because we have no way of sort of applying a unitary to a quantum channel because it is itself, you know, it is itself a super operator. So it doesn't sort of, but that's the sizes of the matrices don't quite work out. So it's not super clear that you can take this thing, which works for states, and turn it into a sort of protocol that can estimate very many things. So you sort of get free lunch in a polynomial number of time, in a polynomial number of copies, I guess. How are we doing on time? Talking about time, quite important. Oh, we're already way over time, so I'm going to be slightly faster.
Well, yeah, the first talk was a bit delayed, so
yeah, that's
true. Can take 5 more minutes or so. That's fine.
So the crux is, can we apply shadow techniques to quantum gates? And it turns out we can. And you know, I've sort of already promised you how to do this. The way we're going to do this is by taking a well-known sort of standard protocol called randomized benchmarking, which is classically sort of quantumly efficient and allows you to extract a single number, so this trace that I mentioned before, of your quantum channel by interspersing it essentially with random unitaries. You can sort of get a decay rate that allows you to estimate this trace. But you can see here, even if you sort of don't get into the details at all, you can see here that this protocol here looks a lot like the one I mentioned before, in the sense that there is sort of a randomization over unitaries here. But instead of randomizing with a single state, I'm randomizing everywhere between subsequent applications of my quantum channel. And the fact that this is efficient and that the previous protocol is efficient sort of gave us the idea of like, okay, why don't we take these two things and sort of, you know, combine them? So what we're going to do is we're going to take randomized benchmarking and we're going to pretend that it generates shadows in the same sense that this randomized measurement scheme for states generates shadows. And we're going to invent something called randomized sequence estimation, where we prepare some state and then we do a random sequence and then we measure, and then sort of in classical post-processing, we're going to sort of revert this operation, but with an extra thing in between that we're going to that we're going to specify. And it turns out that this A is the thing that we can sort of, this is going to take the place of the observable that I mentioned earlier. So it's sort of a quantum channel observable. And it turns out to be quite a useful thing. So this thing we call the sequence shadow. And if you say, okay, these sort of baggy UNs, I didn't have space here, so I had to sort of do some substitution. If you plug in here sort of random unitaries interspersed with our quantum channel that we want to care about, and then we sort of average over unitaries, measure, and compute these sort of classical prefactors, which again, we can sort of do for many different A's with the same set of data. It turns out that this P of M, the sort of abstract function of the number of unitaries, is directly related to not just the trace of lambda, but the trace of lambda times A. So now we're still sort of estimating a very average quantity of lambda, but I'm giving myself the ability to, with a single data set, estimate the trace of lambda times an arbitrary A, as long as I can classically compute it, for using the same set of data for very, very many A's. Because again, by the union bound, I can calculate exponentially many A expectation values using polynomial number of resources. So that's sort of the long and short of it. I can talk about this for hours and why it works. Is actually proving that this takes polynomial time is fairly sophisticated, but we're not going to get into that. I want to very sort of quickly show you what you can do with this and how this goes beyond sort of the standard idea of just estimating traces. So one thing that we can do, because we gather data once and then sort of classically post-process it, what we can do is we can run optimization loops on our reconstructed data purely classically. So we touch our quantum computer once, and then we can do everything else on a classical computer. So imagine that we have some sort of noise model. It's a unitary over rotation, and it doesn't really matter what it is, but the point is that we're going to pretend that it has two free parameters, and we're going to try and see if we can find them by sort of matching the correct A to it. So what we're going to do is we're going to say, okay, A is also this unitary, but with two unknowns in it. And we're going to try and find sort of the point of maximum overlap to sort of maximize this trace. And you can compute sort of you can sort of create these really nice sweeps. And you can see here, these are different P of M's for sort of different values of A. And you can see that sort of the number goes up as we get closer to the correct values of θ1 and θ2. And this is very much a proof of concept, but it's a very flexible idea, because again, you could only need to do this experiment once, and then you can sort of classically start trying to find what these parameters are without having to redo your experiment, which I hope some experimentalists will be happy with. Let's see, we're still in the process of selling it to them. All right, so what are the take-home messages here? Characterization is a fundamental part of near-term and I think also long-term quantum computing, because quantum computers are noisy. This is just a fundamental problem that we have to deal with. And we're a long way away from being able to ignore it. I mean, this doesn't mean that I don't think quantum computers will work. It's just that, this is something that we will have to keep track of, basically, for the next, 24 years. Number two, slightly more specific, this idea of randomized shadows, which is essentially, I think, sort of a mid-2000s classical compressed sensing idea, where if you want to reconstruct a matrix really efficiently, just like apply random vectors left and right. Like, this turns out to be a really good idea. This allows us to get our free lunch. And sort of the broader idea, and this is maybe more of a pitch than a conclusion, is if you know a lot about signal processing, and especially sort of tomography of really large matrices in very particular scenarios, come find me, because I have large matrices and a weird access model, and I need you to help me extract information from these large matrices. All right, thanks.